All right, well, good afternoon. I very much thank the organizers for inviting me to come here and share a few thoughts and ideas with you. The speaker just before lunch, worried about the fact that he was preventing you from getting to lunch. As the first speaker after lunch, I also have to worry that you had a great lunch and now you'll fall asleep. So I have to keep it exciting, or to try and keep it exciting. So when I was asked to come and give a keynote here, I decided to try and sort of pick a couple of ideas. I was probably late in sending them the title of my talk, so I made this up and said, Transformational Innovations to Reduce Maintenance Needs and Extend Pavement Life. And having said that, that's essentially what I'm going to be talking about. The outline for my presentation, I'm going to just give a very quick one-slide motivation for what I'm calling new methods and materials. And then I'm going to talk a little bit about inverted pavements, the philosophy and the construction of inverted pavements. And then I'm actually going to share with you what I think is probably the premier performance data set of inverted pavements in the United States. A particular system I'm going to talk about is a quarry that was built in 2001, a quarry road, I should say. And we have data now. The most recent data was collected earlier this summer, and literally the master's student working with me finished processing some of the data about 10 days ago. So it's hot off the press. No one else has seen it. I'm then going to kind of switch from the system level, the pavement level, and I'm going to go to a component that, for example, is in some existing pavements, but I'm going to take a new approach to it, and that is looking at, for example, the next generation of geogrids. And some of you may be familiar with geogrids. I'll certainly give a little introduction to it. But more importantly, that the reason I'm using that particular example is that I want you to start to think about bioinspiration and what role bioinspiration might also play for you in whether you're a concrete person, whether you're an asphalt person. Bioinspiration is all around there, and some great opportunities. And then I'll finish up with some summary comments. So the motivation, and I knew I wanted to put a slide like this up. In 100% disclosure, I generated this slide in 2013. And so my thought was, oh, I better update that slide. And then as I looked at it, I realized that in the top left, the vast network of roads has changed a little bit, but not probably to the extent that you can tell from the little figure I have there. Yes, there's some additional now funding stories, and maybe there's a nice new peak coming for us, which is good. The one on the reason I didn't change the slide in the end was this is the ASCE infrastructure report card for roads. And in 2013, we scored a D. Now, I have some personal misgivings about the infrastructure report card. I'm not convinced that it's as scientific as I might want it to be. But more importantly, I decided to leave the slide because guess what? In the 2021 ASCE infrastructure report card, roads are still a D. So that tells me, despite perhaps all of the investments we've made, all of the hard work, all of the research we've done, either the report card is getting it wrong, or we somehow are not making the type of transformational changes that we need to make. So with apologies that it's an 8-year-old slide, it actually is not that out of date for a variety of reasons as I've described. The bottom line, though, and most importantly, is if I take those 3 graphics that I have shown there, I think what we need to start to think about is, and we've heard some of them already today, so I don't have a moratorium on them, but I think the key thing is solutions sources are innovative designs, and optimal use of new materials. And so I've actually enjoyed all the presentations so far this morning, whether it's related to characterization or looking at how to different techniques for reinforcement, different techniques for testing and so on. It's been actually a very enjoyable to be part of it. So inverted pavements, say philosophy and construction. So I suspect some of you have at least are vaguely familiar with what inverted pavements are. This is a conventional pavement where you go from a subgrade to an unbound aggregate base to an asphalt base and to an asphalt concrete surface. And interestingly, if you look at the stiffness of those layers, they increase in stiffness as you go from bottom to top. However, an alternative technology that's been out there is what is called inverted base pavements. And you go from a sub-base, there is a cement-treated base, then there's the unbound aggregate base, and then there is the asphalt concrete. And you will notice that now looking at the profile of stiffness, the stiffness is not one that increases from bottom to top, but rather there's a very stiff cement-treated base, second from the bottom of the typical cross-section. And that plays a very important role in then the compaction of the unbound aggregate base. It gives a solid base against which to compact. But there is another part to it as well, which becomes important. And so finally, though, there's clearly, with those two approaches, conventional versus inverted, there's a stiffness contrast between layers, and the granular base is close to the load. And so there's a demand for exceptional performance from that granular base, which perhaps you don't have to be quite as diligent if it's further away. So it's not new. For 50 years, this is a technology that has been around in South Africa in particular. And there's a great history of using inverted base pavements in South Africa. And in fact, many of the early contributions come from individuals like Weinstein and some others. And they really have had exceptional experience with building and utilizing inverted base pavements. US experience, though, has been also quite long, but perhaps the appropriate way to say it is it's been sparse. It tends to have been limited to a number of test sections. There have been individuals through the last 5 decades who have been champions from a technical point of view because they realize potentially the opportunities that maybe are being afforded by inverted base pavements. But maybe one of the things, and I don't want to get into a pseudo-political conversation here, but maybe the biggest thing in the end that has limited the ability of inverted base pavements to really take off here is strong lobbies from certain parties who feel that it's not in their best interest to have a new type of pavement system. I think with time and with continued demonstration, there's going to be successes. And in fact, right now, Federal Highway again is really coming back and revisiting this. Imad El-Kaudi and Errol Tudemuller are in the latter stages of writing an FHWA report. In fact, they're going to be including the data that I'm sharing with you today. But bottom line is, in the US, experiences go all the way back, and there's a list of places here, or mostly places. Even, by the way, going back to, I'm from Georgia Tech, as you know, but back in the 80s, my former colleague, Dick Barksdale, was very much involved in looking at inverted pavements and what potential they brought. In the early 2000s, GDOT put in, Georgia Department of Transportation put in a test section in Morgan County at a quarry access road. I've highlighted that in red today because that's the one I'm going to particularly focus on. There's another test section in Georgia that was put in LaGrange when they were building a new bypass for the Kia auto factory. I'm not going to present the data from that today, but allow me to tell you that it's also exceptional and supports the observations we've made in Morgan County. And then there's several others, the Bull Run, Virginia Highway, the Pineville, North Carolina quarry, and I think there's even actually, I should have put it here, one more in Nashville. Vulcan Materials, for example, has been a strong proponent of this as a potential technology. So a key to, in my opinion, the success of inverted pavements is a technique called slushing. And I'm showing here a little schematic where on the left-hand side, there's an image that says there's no fines. In the middle, there's an image that says there's enough fines. And in the right, the image shows excess fines. And slushing is a technique that has been developed that moves you from a position where you have excess fines to a position where you have just the right amount of fines. You don't want to have insufficient fines, because now what happens is you start to get crushing during performance, you get rutting, you get surface distress and everything. So that part of the compaction process is critically important. And there's a brief description of slushing here, but basically what it involves is not putting the biggest compaction system that you can there, which, by the way, is probably going to change the properties of the material that you carefully measured and characterized before you went to the field. And instead, after the initial compaction, you flood the UAB with water, you roll it at high speed. And the idea is you want to suck the water out and the excess fines, bring it to the surface, so that you end up with a matrix where the coarse particles are in contact with each other and the voids between the coarse particles are filled with fines. And then once the fines come to the surface, you actually brush them off, and you end up with a very well compacted unbound aggregate base. The images on the left just show some of the brushing. Perhaps interestingly enough, the South Africans use a rock hammer test, and when the material has been slushed and compacted and you hit it with a rock hammer, there is a very distinct ping comes from it, and they actually call it the ping test. But it's like literally hitting almost a rock, even though it is a particulate material at that time. So now on to the performance assessment. So a test section was built 21 years ago at the Morgan County Quarry. In total, there was it's 1,800 feet. Actually, how do I find a cursor up here? Maybe I don't with these. Oh, sorry. I'll run without it. Starting at the highway out here, it runs in this direction. And there is initially a 1,000-foot section of conventional pavement. There is a 400-foot section of what's referred to as South African inverted base pavement. So in other words, involves the slushing and everything. And then because Georgia's Georgia, there's also a 400-foot section of what they call Georgia inverted base pavement. And the big difference there is that they didn't do the slushing for the Georgia portion of it. What I'm going to show you is a series of results from this. And I realize some of these may be a little bit small, but you're going to have the presentation so you can come back and look at it. But importantly, what I'm showing here, for example, and you'll see this similar type of plot in several cases in a minute, the blue and the yellow are actually the conventional section. But for a lot of our investigation, we have actually separated that first 400 feet from, 300 feet from the next 700 feet. And the reason being is that within the conventional section, the performance of the portion that's blue was far inferior to the yellow section. And really our understanding is that's because that was at the section right near the highway when the trucks, the outbound trucks, would have been braking heavily. And so the amount of distress is much higher there. And for that matter, the inbound trucks were turning in off the highway, and they were traveling at relatively high speed, and so there was a lot of shear as they turned in off the highway in the first few feet of it. The important thing is that you'll see in all these plots, I'm separating the inbound from the outbound. So the nice thing about this test section was we have the same number of trucks, just on the inbound, they're empty, and on the outbound, they're full. And so we get to even get 2 measurements for every time a truck comes in and out of the quarry. What you can see here is this is initially the falling weight deflectometer measurements, and you can see there are data points for the individual tests, but also I have shown average lines corresponding to the average FWD. This is for a 9-kip drop for the particular section, and then the dash line is for the 2007 measurements that were made, and the solid line is for the 2022. And so you can see, for example, that for the 2 inverted sections, there's almost no change in the FWD responses going from 2007 to 2022. And also, not only is there no change, but they're also very small, the values compared to, for example, the conventional in the yellow, and then more importantly, the conventional by the gate, where they're even higher because of obviously the greater distress that's occurring there. The other parts of our study were done using, some of you are probably familiar with the vehicle that my colleague James Tsai developed over a number of years, and includes both imaging and LiDAR. There's some images here of the vehicle, but also some images captured with it. And so we use that data to then come up with measures of surface distress. I report the results here in terms of the PACES rating, which is what James developed for Georgia DOT. And there's also some data on rutting as well demonstrated here. For the PACES rating, and again, this is for 2016. By the way, I only got involved with this project in 2015. And so as soon as I got in, I was delighted to hear Nina say this morning, you need baseline data. And I said, we have no baseline data. We have a test section here, and other than the falling weight deflectometer that was put in, that was collected 6 years after it was first put in, we have no baseline data on surface distress, on rutting. We need to get a data set. And so as soon as I got involved in the project, we actually went out and did those measurements. And then we just did the follow-up set now 6 years later. And again, you can see that in this case, on the upper is the inbound and the lower is the outbound. And the PACES rating, obviously, what you're interested in here is by and large, higher values are better as far as the PACES rating is concerned. And you can see that the inverteds perform by and large better than the conventional. And in fact, the South African probably is even a little bit better. And again, importantly, if you look at the degradation or the change between the 2016 and the 2022, it's a very moderate change. Even though this is a busy and active quarry, we have actually all the load data and the easels and everything. So I'm not presenting those as part of this today, but we have that. So it's a great data set. We also plotted the surface distress using this PACES rating scheme that James Tsai came up with. The definitions are on the right. And what you can see here is, the light green is load cracking, severity 1. The hashed is load cracking severity 2. The dark green is load cracking severity 3, and the blue is block cracking. And so obviously you may have large block, but not not the worst condition. And so these two plots show the summaries for both the inbound and the outbound. And again, if you look at the contrast between inbound and outbound, you can see that as expected, the outbound has performed or has degraded much more significantly. There's more cracking, there's more damage because you're carrying loaded trucks on the way out. Similarly, we did a rutting study in 2022. We did not have a rutting study in the first time because the LiDAR system on James's truck was or van was not working. But here we have instead of it being 2016 and 2022, we actually have separated the rutting into left wheel and right wheel path, and that's because obviously the right wheel is always going to be closer to the shoulder, the left wheel is towards the center, and this is since it's a quarry access road, you certainly are likely to have some wavering or weaving of the trucks as well as it goes along. But the bottom line is the rutting here, and I realize this scale doesn't perhaps show it quite as well, but in general, the rutting for the South African inverted base pavement again is much less than for others. So concluding observations, the inverted pavements have outperformed the conventional pavements in the Morgan County test sections. Sections of the conventional pavement, to be honest, have failed in line with their design life. The inverted pavements have far exceeded their design life, and actually I would say based on the rate of deterioration and things like cracking and rutting, they can contribute for significantly longer. And remember, these are roads that have been in place now for 21 years, 22 years almost. The inverted section with flushing was used, where flushing was used, appeared to be performing even better than the more conventional compaction of GAB was used. And as I said, similar findings, we've got the same for the Lagrange bypass test section as well, but I'm not presenting that in the interest of time. Okay, so now moving on to some new perspectives on geogrid design. So let me start off by saying, why is bio-inspired design a good fit for geotechnical problems? So that you can say geotechnical transportation problems or pavement problems, if you like. First of all, believe it or not, I can believe it's the source of creative solutions. I think it provides a catalyst to make us question long-held misunderstandings. A lot of times we don't know what we don't know, and therefore we're quite happy tweaking something that we think we know, but in reality, there's a whole vast compendium of ideas out there that we maybe are failing to recognize. The solutions can be versatile and adaptable. Nature is highly adaptable. It wants, you know, motivation for a lot of solutions in nature is survival. We probably don't like to think that we're in a survival mode right now, but maybe we're not so far from survival that paying attention to adaptability is important as well. Sustainable ideas are exposed. We're exploiting information and not resources. We don't adapt solutions just by using more energy. You know, as humans, we're pretty energy agnostic in all honesty, and we think if we're not getting this done, then put your foot on the floor and let's give it a little more gas and we'll get the job done. A great example I think of that always is if you measure the amount of energy used by ants in creating tunnels in the subsurface, they use less than 0.1% of the energy of the most efficient human tunneling machines. We are being outperformed by a bunch of ants, and not just by a little bit, orders of magnitude. Now, I'm not saying we'll ever get to theirs, but boy, if there's plenty of opportunity to at least learn from what they're doing and see if we can't do. And finally, no big surprise, but biological organisms, they comply with nature's environmental and ecological standards. So for today, I'm going to talk about spider webs. If you came to my lab today, tomorrow, you'll see that there are experiments going on that involve worms, tree roots, spiders. What am I missing? It'll come to me in minutes. Ants. Sorry, I already talked a bit about ants. We're not trying to mimic what they're doing. We're trying to learn from them. And so, you know, a question I have is that if I start thinking about some of the fundamental properties of spider webs, and I think about, for example, pavement problems, then I say, could there be a better stress distribution mechanism with other geogrid structures? I'm going to show you some conventional structures that are right now are often used, but let's think about whether there may be something better. And we started off doing some finite element modeling, just of some very simple examples of things that we thought we saw in the spider web. And at the end of that, we sort of got possible insights, for example, things like adding spiral or radial radii to the triaxial geogrid. That's an existing type of geogrid. Could perhaps increase the stiffness. Adding in internal inner hexagonal spiral might uniformly increase the stiffness around 360 degrees, et cetera, et cetera. So by no means were these telling us you need to do this. What they were doing was they showed us things that we saw in the spider webs that we said, why are they doing that? We need to try and either experimentally or computationally study that. And so where better to start than a few spider webs? I'm sure none of you thought that you'd look at a slide on this symposium where there was a spider or several spiders, but I had a couple of undergraduate students and wanted them to do a project. And so I said, okay, find 10 spider webs and characterize them for me. And so they went out and they found them, and then in a consistent manner, they characterized them. And just a couple of examples here. And yes, there's a little bit of variability, but in these two plots here, I'm showing the web angle. So for those 10 spiders, and in the lower one, I'm showing the web rib length. And yes, number 2 is a little bit of an outlier, but by and large, the rest follow each other. And by the way, the lines on that are the blue is the min, the green is the median, and the purple is the max. And just on the right-hand side, again, are some examples of spider webs. I also had them generate histograms of the areas of the openings in the spider webs. And while the numbers vary a little bit, spider web to spider web, you can see that they essentially have a distribution where there's a lot of smaller openings, and then it gradually diminishes in frequency as you get to some larger openings. And keep that general shape of histogram in mind in a minute. The other thing, I'll just summarize some key observations. So there seemed to be in most of the spider webs a condensed center area surrounded by some larger openings, and then it went back to some smaller openings. Generally, the area increases, distance from the center increase. Some of the spiders did have a spiral center. We actually think that the main purpose of that is for when a spider goes to dismantle its web, it actually facilitates the collapse process. And I don't have time to show it today, but I've got a wonderful picture of a spider web at one of the grad students' house. He happened to walk out the door just as the spider was getting to wrap up hunting for the night, and they fully recapture their material, and it comes down in seconds. It's incredible the way they get the spider web to collapse. And finally, approximately 15 degrees between each rib. So then I started to say, well, mimicking spiderweb characteristics within a geogrid line, maybe it's going to increase the peak stress values. Maybe it'll allow us for a better area distribution and introduce new shape patterns. It may involve adding more radial, then that can increase the stiffness, and it may require a little bit more material. Now, the 4 images in the top there are, at least 3 of them you're probably very familiar with if you've been around for any time at all. Those are uniaxial, biaxial, and triaxial geogrids. And the one on the right is just recently been introduced by Tensor. It's called Interax, and that's their new model. Right away, you'll see one thing that's new, and that is that in the 3 on the left, the openings are all the same size. There's one opening size in geogrids historically, right up until, what, 9 months ago when Tensar introduced their Interax, and it's the first one that has a different opening size. In the bottom, here are some of the goofy ideas that those undergraduate students that I had working with me came up with based on the spider webs. I just told them, come up with some ideas that might be our spider web inspired geogrids. And then we went through, we actually 3D printed all of those spider webs, including the existing ones. And then we ran load displacement testing on them. The image on the lower left is just a hexagonal frame that we've held it in. And the most important thing from the graph on the right, the blue line, which is about the lowest load displacement plot, is in fact for triaxial geogrid, which until recently has been the leading geogrid in the market. So clearly room for opportunity. So how do we assess the macro scale response? Well, we've been doing some finite element modeling. This is just a quick image of that. And I'm going to show you results for, I think, these four. Again, it's on the left is biaxial, the next one's triaxial, the next one is Interax, and the one on the right, which I think, by the way, has got the coolest name, is Spiderax. So, I mean, who doesn't want to build a pavement with Spiderax? And so what we've been doing is we've been looking at where we place those geogrids at different elevations within the triaxial samples and apply loading. We're looking at what happens to the form shape. In the plot here, in fact, the upper one on the left is the grids. The grid is placed at the 1/3 point. It's placed at the midpoint in the middle of the plot on the top, and it's placed at the 1/3 from the bottom in the plot on the right. More importantly, in the larger plot at the bottom, we actually put 3 grids in there. And so you can start to quickly see where the presence of the grids actually constrain deformation. And also importantly, the line, the red line, which is to the left, that's the baseline. That's just soil on its own. So what the others are showing you is what? Geogrids. I'm also happy to say that the one on the right, which is the purple, that is Spiderax. And so a spider web inspired geogrid is actually right now, at least based on these tests, for example, outperforming all of the commercial products that are out there. The other thing, though, that we began to realize as we were doing this, and that is here again are the same 4 grids. And many times we look at these grids and we say, oh, they're black and white. And so we look at images of this. You know what? We don't get all the information out of a plot like this that we could. But if I color code them based on the area of the opening, all of a sudden a picture starts to emerge for me. You can see that the 2 on the left, they're all one color because they have one size of opening. The new Interax has 3 colors. There are actually 3 different opening sizes in it. And likewise, the Spiderax that I'm showing here, this particular version of it, has got 3 different colors on it. So all of a sudden, when you start to look at coloring the images, there's a visual story comes that you previously hadn't seen. Importantly, let's come back to the histogram. Remember what the spider web was showing us. They had lots of the smaller openings and then decreasing. So the orange plot here, the orange bar, there's only one orange bar. That is the triaxial grid. The blue is the biaxial to the right. There's only one bar. The Interax is the 3 gray bars, and you can see that there were actually 3 opening sizes. And then the orange, the light orange or the yellow is Spiderax. And importantly, when we look, for example, at the grain size distribution of, for example, a GAB, typical GAB spec from a DOT, that's the range of openings that are typically in that material. And so historically, we have not stopped to think about what should be the right opening size that we have in our geogrids to get the most out of the counterface material. The other thing that I wanted to do, though, was let's blow up these, in this case, just Interax and SpiderAx, Interax on the left. What you will notice is that the nodes at the corners of the hexagon are the connection points, because now I have more than just one unit cell here. I've got a stack of cells here. So the nodes are a point that in the Interax are connected. If you look to the right in SpiderAx, you'll see that there's actually continuity along full rib lengths between, let's say, two brown sections and so on. And so while fundamentally they both have three different particle or opening sizes and they're in a different order, they also result in different configurations when you look at the structure. And if I go one more, so now I'm putting a bunch of those previous slides together, you will start to notice that, for example, Interax still is the same, there's connection points. But what you start to see now in SpiderAx is a secondary structure that is emerging as you look at it, just based on the color. And so we have not finished all of our analysis of this yet, but what it immediately says to you, wow, now I realize why our friends, the bridge engineers many years ago, didn't have all of the openings in the girders or the whatever the same size. That wouldn't have made sense. And all we're doing here is we're putting a truss horizontally in the ground, but for some reason we thought we didn't need to worry about the opening size of the geogrids. And that's a comparison of the large scale ones. And just again, the good news is the orange here is SpiderAx, the gray is Interax, and the blue is the without, so that's just the soil alone. So we are really able to, by stopping and thinking about the design of our grid, do a great job. So quick couple of summary comments. In fact, I've really all said them already, so they'll be in the presentation. So I've got one small set of slides still to go. So I've talked about opening size and used sort of the visualization to get us to there. But now we've also been doing some modeling because we're trying to think about the interaction between the grid and the aggregate, and how are displacements, or how are the grids interacting with the aggregate. And to do that, we switched from FEM to DEM, discrete element modeling. And nominally, I'm showing just three cases here. One on the left is the soil only, or the particles only. In the middle is one with a geogrid at a certain elevation. And then the one on the right with that pink band or that red band, what I've done there is I've said, if I had perfect interlocking between a grid and the aggregate, none of those particles in the pink zone would move. They'd be locked in place. And I can still allow them to move vertically. I can do all that. But that essentially represents the upper bound of what I might be able to expect from the interaction between a geogrid and the particles. And so this is just our test system where we're doing cyclic load, well, both static and monotonic and cyclic loading on the system. Here are some force networks. This is only at 100 cycles. We've done obviously others at higher level, but just for the purposes of this, I pulled just this plot. On the left, you can see the unreinforced. In the middle, you can start to see the the fact that the grid there really starts to narrow down the zone where the primary force networks are below the grid. And then on the right, the perfect zone. It doesn't completely eliminate them, but what it does is it even narrows it further. And this plot here is really a summary of that. The rutting performance on the left, the lower bound here is the soil alone. The upper bound here is that pink zone, showing you that's the best you can hope to do for this particular configuration. Because remember, you've got soil above that locked zone and you've got soil below the locked zone. So they will emerge, they will evolve, they will contribute to surface displacement, they'll contribute to rutting and so on. And then the other ones are actually different configurations where we looked at the different thicknesses of that pink layer compared to the diameter of the particles. These are just the horizontal profiles going from ground surface. Here's where the geogrid is, or the fixed layer, and you can see that again. This is the perfect situation with a fixed layer. This is the unreinforced, and this is with a geogrid. And likewise, these are the vertical displacements when I change. Sorry, these are horizontal displacements in the middle and vertical displacements on the right. More importantly, what we wanted to do was to also say, so what happens when I look at how the force is getting distributed out within the geogrid? Because remember, the role of the geogrid is to essentially confine particles that want to move out when they're subjected to vertical load. And the geogrid is hopefully putting that tensile component, if you like, in there. And so on the left-hand side, there are 3 images showing those the forces in the ribs. The upper one is for triangular, the middle one is for the square grid, and the lower one is actually for a hexagonal grid. We intentionally did a hexagonal because we thought, well, first of all, at the time we were doing this, literally just a few months ago, we were under an NDA to not expose the Interax design, so we did this. But what you can see is, if you look, and particularly at the middle plot, this is the normalized cumulative axial forces. And eventually, when you add them all up and you get far enough away from the point of application, you're going to reach the same point. But what's happening is they are different as you go with a different type of structure. And so this is giving us the insight as to how we may want to try and optimize our spider axe web in the future, so that we put ribs where they're going to do the most work for the particular objective that we have. This is also similar, but now in this case, we're looking at the rib axial stiffness. And in this case, it's all for triaxial grid. So we didn't vary the grid here. We just wanted to look at different axial stiffnesses. And by the way, in both that plot, if you look at the images on the left, those darker purple areas are really where the primary forces are being distributed, and you can see that they're much more concentrated depending on the rib configuration that you're looking at. And so just as a sort of summary of that part, depending on what configuration you pick, you can either be worse or better depending on what the distribution is, and likewise for the axial loads on the right. So some summary comments. Opportunities for innovation are abundant. I think everybody will agree. We have the tools: experimental, numerical, visualization. I have to tell you, I am jealous, and I'm going to try and find a reason that I can get up to Nenad and give him something to put in his magical bridge building, even for just to be able, so I can look at the structure. Importantly, we need to be willing to question existing approaches. And sometimes that's hard for us to do if we're just trying to sit at our desk and be the smartest that we can be. But if we go down to the lab and we watch an ant, or we watch a worm, or we watch a spider, and we say, what the hell are you doing? So first of all, they won't answer you, or if they do, you don't understand the answer. But if you study what they build, what they look at, what they do, you will turn around and you can say, why are they doing that? I need to somehow create a model that I can replicate that, or I need, and it could be a physical model, it can be a numerical model, but I can then understand what they're trying to do. And so today, I am not standing up here to say to you, this is it. On the contrary, I just tried to illustrate with a couple of examples, maybe one that's sort of at the entire pavement level, and one that's at a component of a pavement level, that there are huge opportunities for us to innovate. And maybe in another 10 years, I will have to change that slide number 2 for motivation, because we'll be looking at an infrastructure report card that says we're actually a B or something good like that. So bottom line, there are huge opportunities out there, and I will argue that I'm very realistic myself. And as we say into climate change today, that's only the tip of the iceberg. So I've shown you just a couple of little things today. And with that, thank you very much. And I'd be remiss if I didn't always acknowledge the exceptional students that I have the pleasure to work with. They're the ones that sometimes give me a second look and say, are you really sure we want to do that? And other times they come to me and they say, we should do this. So none of us, I think, would be where we are without great students to work with us. And with that, thank you very much.
Thank you so much, David. Maybe time for just a question or two here before we head to the break. So, any questions at all?
David, very inspiring. I have a question about the efficiency of material usage. For example, for the spider web, each without field grade, you have a better performance than using. That I don't know if that come at a price. You have to use more materials.
So for some of the undergrad student spider webs I showed you, I can assure you, if I tried to convince Tensar to make a grid with that amount of plastic in it, they would shoot me and it would be over. So what we're actually doing though is we're trying to say, you know, how can we optimize? How can we pick certain things and maximize those? You know, one of the things that, again, I think is important to think about when we're reinforcing a pavement, by and large, except for maybe a few drunk drivers, you know, most of the vehicles pass down a certain path within a certain lane. Yeah, they change lanes from time to time, but by and large, compared to the total number of wheel loads, that they're in a certain area. So we don't recognize that when we use a geogrid that is distributing everything uniformly. So for example, can we come back and not be so tied? And that's where, I mean, we actually collaborate very closely with Tensar because they have the manufacturing expertise that we don't. And so discussing ideas with them as we're looking at different options is critically important to us. So, and you saw I have, they were on my, their logo is on my slides because they're very much involved with this research and supporting some of it. So, Lindy.
I think inspiring. Question: did you observe or study the constructing process of the spirals river? So it's kind of starting from that zero at the beginning, and then how they can self-supporting back in that way.
So interestingly, you know, they start with a few radials. That's their MO. They're not. So the spirals or the chords, those are fill-ins. And one of the things I didn't highlight it today, but for example, in some cases, instead of just connecting a chord to the next radial, as they get close to the chord, they will actually put a Y junction. Or when they get close to the boundary of the area that they're filling up, they'll actually put Y junctions. So they understand for stability, at least this is my interpretation, they understand the importance of, for example, struts sometimes to affect the overall stiffness of the structure. So we have a couple of frames in our lab where we have actually observed spiders, and others have done this too, where they've observed spiders building webs. Most of the people who've done it, quite frankly, are not civil engineers, geotech, pavement engineers. They're biologists who are interested in why is the spider doing what the spider doing. I'm interested in why is the spider doing what it's doing, so I can be a copycat and maybe bring it into geotechnical engineering. So.
Okay. no further questions, then I think let's thank David again for his presentation.